In this video, I will explain what access control lists are and how they work. It is a complete video on access control lists. It includes all ACL-related topics that you need to practice for the CCNA exam. It doesn't matter whether you have any previous knowledge of ACLs or not, after watching this video, you can create, implement and verify ACLs more confidently. Access lists work on routers. Routers connect different networks. When a router receives a data packet on its interface, it reads the destination address of the packet and forwards the packet from the interface that is connected to the destination address. This process is known as routing. Routers follow this procedure for all packets. By default, routers do not differentiate between genuine packets and fake packets. Any host that knows the correct destination address can send packets through the router. If an adversary knows the correct destination address, the adversary can also send packets through the router. If you want to allow or deny only certain packets, you have to define the criteria and actions for the packets. Once the criteria and actions are defined and applied, the router processes all packets through the defined criteria and actions. To define the criteria and actions, routers support ACLs. An ACL stands for Access Control List. It is a list of statements. Each statement in ACL is written on a separate line. ACL statements are also called ACL entries. In other words, each line of the ACL is a statement or an entry. An ACL statement consists of criteria and actions. The criteria define the pattern to be matched and the actions define the functions that must be performed when the pattern is matched. An access list is a set of additional commands or instructions that you can instruct a router to perform before forwarding IP packets. Let's take an example to understand how Cisco access lists work. In a network, 4 LAN segments are connected through a router. These segments are students, teachers, staff, and administrators. These segments respectively belong to students, teachers, office staff, and management team. As far as connectivity is concerned, this network is good. All LAN segments can access each other without any issues. The main drawback of this network is security. This network has no security policy. Anyone can access any resource of the network. A student can access the teacher's computer. A teacher can access the principal's computer. This free flow of access makes this network useless. This network will be useful only if it allows only authorized users to access permitted resources. To block unauthorized access, the administrator can configure access lists on the router. Once the access lists are configured, the router will forward only authorized packets. When creating an access list entry, you should keep 3 main factors in mind. These factors are location, direction, and order. Let's discuss these factors in detail. Location. Access lists are applied to interfaces. For example, if a router has 2 interfaces, you can apply different access lists to both interfaces. An interface can only use its ACLs to filter the traffic that passes through it. It cannot use the ACLs of the other interface. If you apply an ACL to an interface that does not process targeted traffic, that ACL will not work. An ACL acts as a sieve. Just as a sieve uses its mesh to filter out liquid or small particles from a mixture, an ACL uses its statements to filter out the desired packets. A sieve can filter the mixture only when you pass the mixture through it. Similarly, an ACL can filter traffic only if traffic is processed through it. Let's take an example to understand how location affects ACL. In this network, 3 segments are connected through the router. Without any ACL, all segments can access each other. Now, the administrator wants to prevent the staff segment from accessing the server segment. For this, he created an ACL and applied it to the F0/1 interface. Will this ACL work? No, instead of blocking the staff segment, this ACL will block the administrator's segment. The F0/1 interface connects the administrator's segment to the server segment. To access the server segment, the traffic of the staff segment neither enters nor exits from the F0/1 interface. Since the traffic of the staff segment does not interact with the F0/1 interface, the ACL applied to the F0/1 interface does not affect it. When implementing an ACL on an interface, make sure that the interface interacts with the targeted traffic. If the targeted traffic does not pass through it, the ACL will not work. Direction. When a router receives a packet on its interface, it reads the destination address of the packet and forwards the packet from the interface that is connected to the destination address. We can divide this process into 3 phases. These phases are entry, process, and exit. In the first phase, the packet enters the router. In the second phase, the router processes the packet. In the third phase, the packet exits the router. We can apply an ACL before the first phase and the third phase. We can't apply an ACL before and after the second phase. If we apply the ACL before the first phase, the router will process the incoming packets through the ACL. If we apply the ACL before the third phase, the router will process the outgoing packets through the ACL. Inbound and outbound ACLs. If you use an ACL to filter incoming traffic, it is called an inbound ACL. If you use an ACL to filter outgoing traffic, it is called an outbound ACL. An inbound ACL cannot filter the outgoing traffic, whereas an outbound ACL cannot filter the incoming traffic. Let's take our example back to understand the effect of the direction on the ACL. To prevent the staff segment from accessing the server segment, the administrator applied the outbound ACL to the F0/0 interface. Although the administrator has applied the ACL to the F0/0 interface, yet the staff segment can access the server. Can you guess what's wrong with this implementation? The F0/0 interface is the default gateway of the staff segment. It receives traffic from the staff segment and forwards it to the server segment. The F0/0 interface is the entry point of traffic. The administrator applied the outbound ACL to filter the incoming traffic. The traffic of the staff segment enters the F0/0 interface. It does not exit the F0/0 interface. An outbound ACL can't filter the incoming traffic. To filter incoming traffic, the administrator has to apply an inbound ACL to the F0/0 interface. Once an inbound ACL is implemented, the interface will filter each incoming packet through it. The interface will permit only the authorized packets. Order. Once the access list is implemented, the router processes each packet through the access list. For each packet, the router checks each entry in the access list from top to bottom until a match is found. Once a match is found, the router executes the corresponding action. It does not check the remaining entries for that packet. If an access list has multiple entries for the same packet, the router will only execute the action of the first entry from the top. For example, if you apply the following ACL on a router, the router will never stop a white car, even if there is an entry in the ACL that blocks the white car. If you want to allow only some hosts from a network, you should add the allow statements first in the ACL. If you add an allow statement below the deny statement of the same criteria, the allow statement will never execute. Let's understand it through our example. The administrator wants to allow only the host 10.0.0.10/8 from the 10.0.0.0/8 network to access the server segment. For this, he created an ACL and applied it to the F0/0 interface in the inbound direction. Afterward, all traffic from the staff section has blocked. Even the host 10.0.0.10/8 has an allowed entry, still the host can't access the server segment. Can you guess why this ACL is not working? When the packets from the host 10.0.0.10 enter the F0/0 interface, the interface checks the applied ACL. The first statement of the ACL says deny all incoming traffic. Since this criterion matches all incoming packets, the interface never checks the next statement for any incoming packet. It always executes the action of the first statement. Since the action of the first statement is the deny all incoming packets are denied. To fix this issue, the administrator needs to put the allow statement before the deny statement. The correct ACL is the following. Allow 10.0.0.10/8 deny all. Now, when packets from the host 10.0.0.10/8 enter the F0/0 interface, the interface will allow them. But if it receives packets from other hosts, it will discard them. Let's understand why this will happen. When a packet enters the interface checks the ACL. The first statement of the ACL is for the host 10.0.0.10/8. The interface will check the source address of the packet. If the source address of the packet is 10.0.0.10/8, the interface will execute the action of the first statement. The action of the first statement is allow. Because of this, the packet will be allowed. If the source address of the packet is not 10.0.0.10/8, the interface will check the next statement. The next statement is deny all. This will match all incoming packets. The action of the second statement is deny all. Because of this, the packet will be discarded. Thus, apart from the packets of the host 10.0.0.10/8, all incoming packets will be discarded. Now, we have discussed and learned how the three main factors of the ACL work. Let's take our example back to understand how these factors affect the ACL implementation. In our example network, all LAN segments can access all LAN segments. To block students from accessing resources outside the student's segment, the administrator created an access list and applied it to the F0/0 interface of the router. The ACL has the following entry. If a packet has the source address from the network address 10.0.0.08, then discard the packet. Since all packets generated from the student's segment have source addresses from the 10.0.0.0/8 network, they will be blocked as soon as they enter the F0/0 interface. After this ACL, users from the student segment will not be able to access outside resources. But they will be able to access all resources available in the student segment. To understand how the location affects the ACL, let's suppose the administrator applied the above ACL to the F0/1 interface. Now, this ACL is useless. This ACL instructs the router to block a packet if it arrives from the 10.0.0.0/8 network. A packet from the 10.0.0.0/8 will never enter from the F0/1 interface. The F0/1 interface is the default gateway of the teacher's segment. Since the network address of the teacher's segment is 20.0.0.0/8, all packets entering F0/1 will have a source address from the network 20.0.0.0/8. This example shows how the correct location of the ACL is important. An ACL must be implemented on the interface that interacts with targeted traffic. Now suppose, instead of using the source address in the ACL entry, the administrator mistakenly used the destination address. The modified ACL says, if the destination address of a packet is from the network 10.0.0.0/8, discard the packet. The administrator applied this ACL to the F0/0 interface of the router. Will this ACL work? No, this ACL will not work. This ACL instructs the router to block the packets that are going to the network 10.0.0.0/8, not to the packets that are coming from the network 10.0.0.0/8. If you apply this ACL to the F0/0, the student segment will be able to access all three segments, but they will not be able to access the student segment. Thus, an ACL must be implemented in the correct direction to filter the targeted traffic. As mentioned earlier, for each packet, the router checks ACL entries from top to bottom until a match is found. Once a match is found, it does not check the remaining entries for that packet. Let's understand this factor through the example. The administrator wants to allow a user from the teacher's segment to access the printer available in the staff segment. The IP address of the allowed user is 20.0.0.3/8. Apart from the allowed user, all remaining users must not be able to access the staff segment. For this, the administrator created the following ACL and applied it to the F0/1 interface of the router. Drop the packet if its source address belongs to the network 20.0.0.0/8. Allow the packet if its source address is 20.0.0.3/8. Will this ACL work? No, this ACL will block all outgoing traffic from the teacher's segment. When a packet originated from the host 20.0.0.3/8 reaches the router checks the entries of the applied ACL until a match is found. The first line of the ACL says drop the packet if its source address belongs to the network 20.0.0.0/8. Since the IP address 20.0.0.3/8 belongs to the network 20.0.0.0/8, the statement becomes true. The router executes the action that is associated with the first statement. Since the action of the first statement is the drop, the router drops the packet. Even the second line of the ACL allows the host 20.0.0.3/8, but it will never be read and executed by the router. The correct order to allow the host 20.0.0.3/8 will be the following. Allow the packet if its source address is 20.0.0.3/8. Drop the packet if its source address belongs to the network 20.0.0.0/8. Now, this ACL will allow all packets originating from host 20.0.0.3/8, but it will block all packets originating from other hosts in the network 20.0.0.0/8. Thus, the correct sequence of the statements in the ACL is important. There are mainly two types of access control lists, standard and extended. You can further classify these types into two subtypes, numbered and named. A standard access list can be either a numbered standard list or a named standard access list. Similarly, you can have a numbered extended access list or a named extended list. Beginning with iOS version 12.3, Cisco introduced a new feature to edit existing ACLs. This feature is called the sequence editing feature. You can further classify ACLs based on this feature. Let's discuss the properties, characteristics, and functions of ACL types and understand how each type differs from the others. Standard access lists. Standard access lists are easy to configure. But they support limited options in entries. In a standard access list entry, you can use only the source address to define the criteria. Apart from the source address, you can't use any other option. Standard access lists work on an all or none formula. They will either allow or block all traffic from the source host. You cannot allow or deny only certain types of traffic from the source host. Since standard access lists work with all traffic originating from a host, they are applied closer to the destination. Extended access lists. Extended access lists are complex. But they support many options in entries. In an extended access list entry, you can use a source address, a destination address, protocol, traffic type, application, and port to define the criteria. Extended access lists allow you to target a specific type of traffic. You can allow a certain type of traffic while blocking the remaining traffic, or you can block a specific type of traffic while allowing the remaining traffic. Since extended access lists work with a specific type of traffic, they are applied closer to the source. Numbered and named ACLs. Routers support multiple ACLs. You can create as many ACLs as you want. To differentiate between ACLs, routers use a unique number and name for each ACL. You may consider these numbers or names as identification numbers or names. When creating an ACL, you must specify an identification number or name for the ACL. Since the router uses this number to identify the ACL, you cannot choose a random number for the ACL. You have to choose a number from a predefined range. Routers reserve the following number ranges for standard access lists and extended access lists. Numbers are a bit difficult to remember. They also do not provide any descriptive meaning. If you have multiple ACLs, it becomes very difficult to remember which ACL is doing what. To make ACLs management easier, routers also support names for ACLs. It means you can also use descriptive names for ACLs instead of predefined numbers. No matter whether you use a name or a number for the ACL functions the same way. As far as functionality is concerned, named ACLs and numbered ACLs are the same. The main advantage of a named ACL over a numbered ACL is that a named ACL is easier to manage and remember than a numbered ACL. Let's take an example. You check the configuration of a router and find the following ACLs. To figure out what these ACLs are doing, you have to check the entries of each ACL. Now, suppose you read the configuration of another router and find the following ACLs. By looking at these ACLs, you can get an idea of what each ACL is doing. For example, by looking at the name blocking students, you can guess that this ACL would be blocking traffic from the students segment. By using a descriptive name, such as block external users, a network administrator can easily determine the purpose of the ACL. This feature is especially helpful in large networks, where a router may have multiple ACLs with hundreds of statements. Advanced Sequence Editing ACLs. Advanced Sequence Editing is a new feature. Before this feature, editing or updating ACL entries was not possible. To edit an ACL entry, you had to recreate the entire ACL. This feature allows an administrator to change, update, or delete a single entry from an ACL. This feature was added later to Cisco iOS. All new iOS versions include this feature. If the iOS includes this feature, you can use this feature to edit both types of ACL. ACLs are not simple. They are one of the most complex features of the router. They only work when they are applied properly. An incorrectly applied ACL can lead to the opposite or strange results. For example, if you have created an ACL to block a certain type of traffic but have implemented it on an interface that does not interact with that traffic, then this ACL will not work. To get the desired results from ACLs, you need to build and implement them properly. There are some basic principles and rules for creating and implementing an ACL. Understanding these rules and principles will help you create and enforce ACLs more effectively. ACLs are implemented in 2 steps, creating and activating. In the first step, you create an ACL. In the second step, you apply it to an interface. Until you apply it to an interface, it remains in an inactive state. An access list does nothing in its inactive state. To activate an ACL, you have to apply it to an interface. You can apply an ACL in 2 directions, inbound and outbound. If you apply the ACL in the inbound direction, it will filter the incoming traffic. If you apply the ACL in the outbound direction, it will filter the outgoing traffic. You can apply only one ACL per interface per protocol per direction. For example, you can apply only one ACL to filter incoming IP traffic on an interface. When applying an ACL to an interface, you have to specify the direction in which you want to filter the traffic. Once an ACL is applied to an interface, the interface processes all packets through the ACL. For each packet, it checks all ACL entries from top to bottom until it finds a match. If it finds a match between the packet and the entry, it executes the action defined in the entry. If it does not find the match, it checks the next entry. If the next entry matches the packet, the interface executes the action defined in the next entry. If the next entry does not match the packet, the interface will keep checking entries until it finds a match. Let's understand this process through this example. It is a red packet. It will always be allowed. The router will never check the second line for red packets. The router will check the second line only if the packet is not red. It is a blue packet. Since it is not a red packet, the router checks the second line of the ACL. The second line discards the blue packet. It is a brown packet. Since it is not a red packet, the router checks the second line. The second line matches only blue packets. Since the packet cannot be processed by the second line, the router checks the third line. The third line allows brown packets. Since the action for brown packets is allowed, the router allows it. It is an orange packet. Since it is not a red, blue, or brown packet, it will not be processed by the first, second and third line. The fourth line of the ACL discards all packets. Because of this line, all packets they are not processed by the first, second, and third lines will be discarded. Once the interface finds a match for the packet, it does not check the remaining entries for the packet. For example, if you have 2 entries, one denying a host and one permitting the same host, the router will execute the action of the entry that appears first in the ACL. It will never read the second entry for the same host. Since the order of entries is important, you should always place the most significant entries at the top of the list and the least significant entries at the bottom of the list. This arrangement will improve the router's performance because most of the time a match will be available at the top of the list, and once a match is found, the router will not check the remaining entries. If a router goes through the entire list and does not find a match in the ACL entries for a packet, the router drops the packet. This aspect is known as implicit deny. Implicit deny is an invisible deny-all statement at the end of every ACL that drops all traffic that does not match any of the preceding statements in the ACL. Because of the implicit deny, every ACL should have at least one permit statement, otherwise, an ACL with only deny statements will drop all traffic. Let's take an example. A segment 10.0.0.0/8 is connected to the F0/0 interface. You want to block only the host 10.0.0.10/8 from this segment. Since you want to block only one host, you created an ACL with a single entry deny 10.0.0.10 and applied it to the F0/0 interface in the inbound direction. Can you guess what will happen in this scenario? This ACL will block all incoming traffic on the F0/0 interface. Let us understand why this would happen. If the packet arrives from the host 10.0.0.10, the deny statement will block the packet. If the packet arrives from the other host, the criteria of the first statement will not match, and the interface will check the next statement to match the packet. Since there is no next statement, the interface will execute the implicit deny statement. The implicit deny statement blocks all packets. This way, all incoming packets will be blocked. To fix this problem, you have to add one more entry just after the first entry. In this entry, you need to write an allow statement for the network 10.0.0.0. After this change, the ACL will block only the host 10.0.0.10 while allowing all reaming hosts from the segment. A new entry is always placed at the bottom of the list. Once you have added an entry, you cannot edit, modify or delete it. If you want to change an entry, you have to delete the existing list and recreate the entire list. Since modification is not allowed, you should create ACL entries on a text editor. After creating them on a text editor, you can copy them to the router. To edit or remove an entry from the existing ACL, copy all entries into a text editor, modify the entries, and copy the updated entries back to the router. This restriction does not apply to routers that support a feature called sequence editing. If a router supports the sequence editing, you can edit or remove a single entry from the existing ACL. There are 8 types of ACLs. These types are standard numbered, standard named with the sequence editing feature, standard named with the sequence editing feature, extended numbered with the sequence editing feature, and extended named with the sequence editing feature. To create and configure these access lists, we have 2 commands. These commands are access list and IP access list. The main difference between both commands is the first command supports only 2 types, the standard numbered and extended numbered, while the second command supports all 8 types. Let's understand the arguments, options, and parameters of both commands. This is a global configuration mode command. This command allows us to create a standard numbered ACL and an extended numbered ACL. This command uses the following syntax. Let's discuss this syntax. It is a numerical argument. The router uses this number for the following purposes: to identify the protocol that will use the ACL to filter the traffic, to identify whether it is a standard ACL or an extended ACL, to group all the statements in the ACL. The ACL specifies a range of numbers for each network layer protocol. For the IP protocol, it specifies the following ranges. From these ranges, the ranges 1 to 1999 and 1300 to 1999 are used for standard access lists, and the ranges 100 to 199 and 2000 to 2699 are used for extended access lists. To create an IP access list, you must specify a number from the predefined number ranges. For example, to create a standard IP access list, you can choose any number between 1 to 1999 and 1300 to 1999. Similarly, to create an extended IP access list, you can select any number between 100 to 199 and 2000 to 2699. While selecting a number for the ACL, you must follow the following 2 principles. To create a new ACL, use an unused number from the range. If you use an existing number, the router will append the ACL related to the specified number. To update an existing ACL, specify the number of the ACL. If you use a new number, the router will create a new ACL. If you are using Cisco Packet Tracer to practice ACL-related topics, you should know that Packet Tracer includes only essential ranges of numbers for the IP protocol. It does not include the extended range of numbers. To view or use all ACL numbers, you can use GNS3 or a real router. Let's use this command on GNS3. As you can see here, GNS3 includes all ranges for all protocols. It is not a bug or an error in Packet Tracer. It is a feature that allows Packet Tracer to run multiple devices on less hardware configurations. Packet Tracer simulates networking devices. In the simulation process, the software includes only the required features and functions of the physical device and the virtual device. Packet Tracer was mainly developed for students. It includes all features and functions that you need to practice CCNA exam topics. For example, you need extended ranges only when you want to create more than 99 standard or extended ACLs on the same router. No CCNA exam topic requires you to create more than 99 standard or extended ACLs on a single router. If you want to create a complex network with hundreds of ACLs on every router, you can use GNS3 or real routers. No matter how many ACLs you create on a router, they all use the same configuration style. To keep this tutorial simple, I will use Packet Tracer in this video. But you can use any software of your choice. The process of creating and implementing ACLs is the same on all platforms. The next parameter in the command syntax is an option with two values. If you use the permit option, the router will allow the packet that matches the condition defined next to it. If you use the deny option, the router will block the packet that matches the condition defined next to it. The next parameter is the conditions. The router uses conditions to match the packet. A standard ACL and an extended ACL use different criteria to match a packet. The available options in this section depend on the value of the ACL argument. If you have specified a number that belongs to the standard ACL, the command will use the following syntax. If you have specified a number that belongs to the extended ACL, the command will use the following syntax. Let's first discuss the criteria of a standard access list. We have already discussed the options and arguments till the action option. Now, let's discuss the remaining arguments and options. Source IP address. It is an argument. It accepts the source address. You can use a host address or a network address. If you use a host address, the router will match that particular host. Or if you use a network address, the router will match all hosts of the specified network. Wildcard mask. It is also an argument. It allows us to define the type of the source address. You can define a particular IP address or a range of IP addresses. It is the most complex and confusing option of the access list command. Let's understand this option in detail. Wildcard masks are used to define criteria in ACL statements. Wildcard masks allow an administrator to define a single IP address or a range of IP addresses. Without wildcard masks, you have to create an entry for each IP address. With wildcard masks, you can create a range of IP addresses that need the same actions. Let's take an example. A subnet includes 75 IP addresses. From these IP addresses, you want to block 50 IP addresses. Without wildcard masks, you have to create 50 entries to block these IP addresses. With wildcard masks, you can create a range that includes these IP addresses. Later, you can use this range to define criteria in the entry. This way, you can block or allow a range of IP addresses with a single entry. Both wildcard masks and subnet masks are used with IP addresses. They look similar, but they are different, and are used for completely different purposes. A subnet mask is used to separate the network address from the host address in an IP address. A wildcard mask is used to define the part of the IP address that you want to match in the ACL statement. Both the wildcard mask and the subnet mask have a length of 32 bits. A bit has two states, on and off. In binary, the on state is written as 1, and the off state is written as 0. In the subnet mask, an on bit represents the network bit while the off bit represents the host bit. In the wildcard mask, an on bit represents the bit you want to match while the off bit represents the bit you want to ignore. In a subnet mask, an on bit represents the network bit, and an off bit represents the host bit, while, in a wildcard mask, an on bit represents the bit to ignore, and an off bit represents the bit to match. By using an opposite bit at each location, you can easily convert a wildcard mask to the subnet mask and a subnet mask to the wildcard mask. This process is much easier than it looks. To create a wildcard mask for a subnet, all you need to do is reverse the value of the subnet mask. If the subnet mask contains the value 1, then use the value 0 in the wildcard mask. If the subnet mask contains the value 0, then use the value 1 in the wildcard mask. Let's take an example. The following address represents a subnet. This subnet includes the IP addresses from 10.0.0.0 to 10.255.255.255. To create an ACL statement that matches this subnet, we have to use a wildcard mask that ignores all network bits but matches all host bits of the subnet address. To ignore all network bits in the wildcard mask, we have to use the value 1 at the place of each network bit, while, to match all host bits, we have to use the value 0 at the place of each host bit. Let's take some more examples. In this subnet mask, we have all ones in the first byte. So we will put all zeros in the first byte of the wildcard mask. In this subnet mask, we have all ones in the first and second bytes. So we place zeros in the first and second bytes of the wildcard mask. Same way, in this subnet mask, we have ones at the first 24 places. So we will change the first 24 bits to 0 in the wildcard mask. If you have subnet masks in decimal and want to create wildcard masks for them, you do not need to convert them into binary. Creating wildcard masks in decimal is also easy. To create a wildcard mask for a given subnet mask, subtract the value of each byte from 255. Let's take an example. Suppose you want to create a wildcard mask for the subnet mask 255.255.0.0. If we subtract each byte of this subnet mask from 255, we will get the wildcard mask for this subnet mask. Let's take some more examples. In the first example, if we subtract 255 from 255, we get 0. Therefore, we will put 0 in the first byte. If we subtract 240 from 255, we get 15. Hence, we will write 15 here. For the third and fourth bytes, if we subtract 0 from 255, we get 255. Therefore, we will write 255 in the third and fourth bytes of the wildcard mask. In the second example, 255 minus 255 equal to 0. So, we will write 0 here. And here. In the third byte of the subnet mask, we have the value 16. If we subtract 16 from 255, we get 239. Therefore, we will write 239 in the third byte of the wildcard mask. 255 minus 0 equals 255. So, we will write 255 in the fourth byte. In the third example, if we subtract 255 from 255, we get 0. Therefore, we will write 0 in the first, second, and third bytes. In the fourth byte of the subnet mask, we have the value 128. If we subtract 128 from 255, we get 127. So, we will write 127 in the fourth byte of the wildcard mask. ACL statements use wildcard masks to define criteria. To identify which statement filters which address or address range, you need to calculate the subnet mask from the wildcard mask used in the statement. To calculate the subnet mask in binary, use the opposite bit at each place. For example, if you have 1 in the wildcard mask, use the 0 in the subnet mask. Or if you have 0 in the wildcard mask, use the 1 in the subnet mask. Let's take some examples. To convert this wildcard mask into the subnet mask, change these zeros and ones. And these ones and zeros. In this example, change these zeros and ones. And these ones and zeros. In this last example, we need to change these zeros and ones. And these zeros and ones. To calculate the subnet mask in decimal, subtract each byte of the wildcard mask from 255. For example, if we have 239 in a byte of the wildcard mask, we will use 16 in the byte of the subnet mask. Because, if we subtract 239 from 255, we get 16. Let's take some examples. 255 minus 0 equals 255. 255 minus 15 equals 240. 255 minus 255 equals 0. If we subtract 0 from 255, we get 255. So, we will write 255 here. And here. 255 minus 239 equals 16. Therefore, we will write 16 in this byte. 255 minus 255 equals 0. 255 minus 0 equals 255. Hence, we will write 255 here. Here. And here. If we subtract 127 from 255, we get 128. So, we will write 128 here. There are two special wildcard masks, 0.0.0.0 and 255.255.255.255. A wildcard mask of 0.0.0.0 instructs the router to match all 32 bits of the address. This wildcard mask is called a host mask. This wildcard mask is used to match a single host. For example, if you want to allow or deny a specific host from a segment, you can use this wildcard mask to match the IP address of that host. The following statement shows how this wildcard mask is used. The above statement will deny only the packets that are originated from the host 10.0.0.1. A wildcard mask of 255.255.255.255 instructs the router to ignore all 32 bits of the address and match all packets. This wildcard mask is used to match all packets. Since this wildcard mask matches all packets, the IP address that you enter with this mask does not matter. Technically, you can enter this wildcard mask with any IP address, but usually, it is used with the IP address 0.0.0.0. Administrators use the following IP address and wildcard mask to match all incoming or outgoing packets. Now we know what a wildcard mask is and how we can use it correctly in the access list command. Let's move back to the access list command syntax. Log. It is an optional parameter. If you specify this parameter, the router will print any match of this statement on the console port. By default, the router does not print log messages on a non-console connection. For example, if you use a VTY connection, you will not see log messages on the console port. If you want to see log messages on a non-console connection, you have to use the terminal monitor command. This command works on the current session only. It means you have to execute this command each time to see logging messages on your VTY or TTY session. For debugging and security purposes, you can also forward these messages to a syslog server. We have discussed the criteria of the standard access list. Now let's understand the criteria of the extended access list. Unlike a standard ACL that supports only the source address, an extended ACL supports many options in the condition field. An extended ACL allows you to filter traffic based on supported IP protocols. The options available after this argument depend on the protocol you select. For example, if you select the IP protocol, you will see the options for the IP protocol. Or if you select the TCP protocol, you will see the options for the TCP protocol. CCNA exam syllabus includes 4 IP protocols. These protocols are IP, TCP, UDP, and Icmp. Before we discuss the options of these protocols, let's understand the type of filtering. There are two types of filtering: host-level filtering and application-level filtering. Host-level filtering is used to filter all the traffic from the host. Application-level filtering is used to filter specific traffic from the host. For example, if you want to filter all traffic from a host, you would use host-level filtering. But if you want to filter only web traffic from the same host, you would use application-level filtering. In simple terms, host-level filtering checks whether host A is allowed to access host B, while application-level filtering checks how much host A is allowed to access host B. Let's discuss how to configure both types in detail. To filter all the traffic from the host, we use the IP address of the host. To use an IP address, we need to specify the IP keyword here. The IP keyword instructs the command that we want to filter the traffic based on the host address. After the IP keyword, we have two fields to specify the source address and the destination address. We can specify a single host address or a range of IP addresses in both fields. We can use wildcard masks with both addresses. To filter a specific type of traffic coming from a host or going to a host, we use the name of the protocol that transports the traffic. On an IP network, an application can send its traffic by using one of two protocols. These protocols are TCP and UDP. To filter traffic based on an application, we use the following syntax. Both protocols can simultaneously transport data of many applications. Both protocols use a unique number for each application to keep its data separate from other applications. These numbers are known as port numbers. Both protocols use different port numbers for applications. For CCNA exam, you should know the following port numbers. The established keyword allows traffic to pass through only if it is generated from inside. It is used only with TCP packets. With this keyword, we can control the direction of the data flow. If we use this keyword, the ACL will allow only those TCP packets which have the established flag bits set in their header. The log keyword instructs the router to log a message every time an ACL entry is hit. As I mentioned earlier, for the CCNA exam, you should know how to filter traffic of 4 protocols. These protocols are IP, TCP, UDP, and Icmp. We have already discussed IP, TCP and UDP. We use the IP protocol to filter host-level traffic. We use TCP and UDP protocols to filter application-level traffic. Now let's understand the Icmp protocol. Sending a packet is not a guarantee of the packet being delivered. Sometimes packets get lost on the way to the destination. In such a case, the nearest device sends the error message back to the sender. From the message, the sender can know about the undelivered packets and their possible reasons. Networking devices use the Icmp protocol to send error messages. An adversary may use the Icmp protocol to reveal information about the network. Extended access lists allow us to control what error messages devices can send. To filter Icmp error messages, the command uses the following syntax. If we do not specify a particular message type, ACL will match all message types. The following table lists some of the most common Icmp messages. You can create an access list in 2 styles, classic style and modern style. The classic style does not support the editing feature. The modern style supports the editing feature. If you use the classic style to create an ACL, you will be able to append it, but you will not be able to modify it. If you use the modern style to create an access list, you will be able to append, edit, and modify it. The classic style uses the access list command. The modern style uses the IP access list command. Just like the access list command, the IP access list command is also a global configuration mode command. It uses the following syntax. This option specifies the type of ACL. To create a standard ACL, select the standard option. To create an extended ACL, use the extended option. To create a standard access list, use the following syntax. To create an extended access list, use the following syntax. The next parameter specifies the number or the name of the ACL. The router uses this number or name to group all statements. Instead of using a number, you should use a name here. A clear and descriptive name makes ACL management easier. For example, suppose you find an ACL 126. The number 126 does not tell anything about the ACL. But if you find an ACL with a name like block sales, you can easily guess the purpose of the ACL. Let's take some examples of this command. To create a standard ACL with the number 34, we will use the following command. The following command creates a standard ACL with the name block production. The following command creates an extended ACL with the number 136. To create an extended ACL with the name allow HTTP traffic, we will use the following command. When you hit the enter key after specifying the name or the number, the command prompt changes, and you enter ACL configuration mode. The command prompt depends on the value of the standard or extended option. If you have selected the standard option, you will get the following command prompt. If you have selected the extended option, you will get the following command prompt. In ACL configuration mode, you create and manage statements. The options available to create statements depend on the type of ACL. If you have selected the standard ACL, the following options will be available. If you have selected the extended ACL, the following options will be available. The access list command and the IP access list command use the same options to build and add an entry to the access list. We have already discussed these options in detail. Let's understand the main differences between the access list and the IP access list command. Both commands use different configuration styles. The access list command uses a flat configuration style. It uses a single syntax to create and manage an ACL and the ACL's entries. It can create only numbered ACLs. You can only append numbered ACLs. You cannot use it to edit ACLs. The IP access list command uses a hierarchical configuration style. It uses different syntaxes to create and manage an ACL and the ACL's entries. It creates and manages ACLs in global configuration mode. To manage ACL entries, it uses sub-configuration mode. You can use it to create and edit both the numbered and named ACLs. You have three options to create a standard ACL. You can use the access list command to create a numbered standard access list. Or you can use the IP access list command to create a numbered or a named standard access list. Let's create 3 example standard access lists by using each option. I am using Packet Tracer to demonstrate ACL creations and the configuration process. You can use any network simulator software you prefer to follow this video. If you have a real Cisco router, you can also use that for practice. The process for creating, testing, and implementing ACLs is the same on all platforms. To use a router on Packet Tracer, we need to drag it to the workspace. Drag the router to the workspace. Double-click the router. Click CLI and wait till the router boots. When the router starts, it checks the startup configuration. If it does not find the startup configuration, it starts the initial setup wizard. The setup wizard allows you to configure some essential settings. We don't need to run this wizard. To create a standard access list, we need to enter global configuration mode. First, we will use the access list command to create an ACL. The access list command needs the ACL number as the first argument. Since we are creating a standard access list, we will use a number between 1 to 99. After the ACL number, we need to specify the action. The router will take this action if the packet matches the given condition. Let's suppose we want to allow all packets from a network. For this, we will use the permit option here. In the last, we need to specify the network address and wildcard mask of the network. When we hit the Enter key, the router checks the running configuration. If it finds an existing ACL having the number 10, it will add this entry to the existing ACL at the bottom. If it does not find an existing ACL 10, it creates a new ACL, sets its identification number to 10, and adds the entry to it. We have 2 commands to view access lists: the Show Access Lists and the Show IP Access Lists. The Show Access Lists command displays all access lists from all protocols. The Show IP Access List command displays all access lists only from the IP protocol. By default, both commands show all ACLs. If you want to view only a specific ACL, you can specify the name or number of the ACL as the argument to the command. Let's add one more entry to this ACL. Since we are adding a new entry to an existing ACL, we will use the number of the ACL which we want to update. This entry will block all traffic from network 20. To verify this entry, let's switch back to privileged mode. The access list command places the new entry at the bottom of the ACL. Now, let's add one more ACL. This time, we will use the IP access list command. Unlike the access list command that automatically detects the ACL type from the ACL number, the access list command needs you to manually specify the type of the ACL as the first argument. After specifying the ACL type, we need to assign a unique identity to the ACL. To create a new numbered ACL, we need to use a number from the predefined range. For example, to create a standard numbered ACL, we need to use a number between 1 to 99. Unlike the access list command, the IP access list command does not use the same syntax to add entries. When you hit the Enter key, the command enters sub-configuration mode. In sub-configuration mode, you can add ACL entries. Let's add 2 ACL entries. This entry allows all hosts of network 30. This entry blocks all hosts of network 40. To verify this ACL, we can use the Show Access Lists or Show IP Access Lists commands in privileged mode. It is the access list that we have created. We can also specify the ACL number to view only this ACL. Let's create one more standard ACL. This time we will create a named standard ACL. To create a named standard ACL, we need to specify a unique name for the ACL. The IP access list command uses the same sub-configuration mode for numbered and named ACLs. Let's add 2 ACL entries. This entry will block the host 60.0.0.1. This entry will allow all hosts of the network 60. On a real router or GNS3, you do not need to go to privileged mode each time to run the show commands. You can run them from any mode with the do command. Since the do command is not available on Packet Tracer, we have to enter privileged mode each time to run the Show IP Access List command. Now we have 3 ACLs. This is the numbered ACL. We used the access list command to create it. This is again a numbered ACL. But we used the IP access list command to create it. This is the named ACL created by the IP access list command. Beginning with iOS version 12.3, Cisco introduced a feature called sequence numbering. This feature automatically adds a sequence number to each ACL entry starting with 10, using increments of 10. To know whether a router has this feature, you can check the iOS version number or use the Show Access List command. To check the iOS version, you can use the Show Version command. For example, the version of this iOS is 15.5. It will automatically add a sequence number to each ACL entry. To check ACL entries, you can use the Show Access Lists command. If you see sequence numbers before entries of an ACL, you can edit the ACL. To edit ACL entries, you have to use the IP access list command. You cannot use the access list command to edit ACL entries. No matter which command you use to create an ACL, if its entries have sequence numbers, you can edit them by using the IP access list command. For example, we created ACL10 by using the access list command, and its entries have sequence numbers. We can edit this ACL. Let's add one more entry before the first entry. To add a new entry before an existing entry, we have to specify a lower sequence number as the first argument. The sequence number of this entry is 10. We can use any number lower than 10. Since we are using a lower sequence number, the router will place this entry before the first entry. To verify it, you can use the show access list command again. You can also specify the ACL number to view this ACL only. As you can see here, the router added the new entry before the first entry. An ACL does nothing until we apply it to an interface. To apply an ACL to the interface, we need to enter interface configuration mode. For example, if we want to apply ACL20 to the Gigabit Ethernet 0/0/0 interface, we need to enter the interface configuration mode of it. No matter whether you use the access list or IP access list command to create an ACL, the command to apply the ACL is the same. To apply an ACL, we use the IP access group command. We need to specify the ACL number or name and the direction in which we want to apply the ACL. For example, to use this ACL to filter incoming traffic, we will use the in option here. To verify the implementation, you can check the running configuration. To view the running configuration, you can use the show running configuration command in privileged mode. As you can see here, the router has applied ACL20 to the gigabit interface in the inward direction. If the ACL entries have sequence numbers, you can delete a single entry from the ACL. For example, let's delete this entry. To delete a specific entry, we use the no command in the sub-configuration mode of the IP access list command. Since we want to delete an entry from ACL10, we will enter the edit mode of this ACL. We need to use the sequence number of the entry here. The sequence number of the entry that we want to delete is 10. So we will use number 10 here. To verify that the entry has been removed, we can use the show access lists command again. As you can see here, the entry has been deleted. To delete an ACL, we use the no command in global configuration mode. Let's delete the ACL block sales. The no IP access list command deletes the entire ACL. You should use this command only when you want to delete the entire ACL. If you want to delete only a single entry from the ACL, use the sequence number of the entry with no command in sub-configuration mode. The no command in global configuration mode deletes the entire ACL. To verify it, you can use the show access lists command again. As you can see here, ACL block sales has been deleted. Just like the standard access lists, you have three options to create an extended access list. You can use the access list command to create a numbered extended access list. Or you can use the IP access list command to create a numbered or a named extended access list. The process of creating and managing extended access lists is the same as the process of creating and managing standard access lists. Let's create a numbered extended access list using the access list command. Since we are creating an extended access list, we need to use a number from the predefined range of numbers for the extended access list. Next, we need to specify the action. After the action, we need to specify the type of filtering. If we want to filter all IP traffic, we will use the IP keyword here. Or if we want to filter the traffic of a specific application, we will use the protocol of the application. Unlike a standard access list that uses only the source address to filter the traffic, an extended access list supports both the source and destination addresses. This entry will allow all traffic coming from network 80 and going to network 90. Let's add one more entry. This entry will block all traffic coming from network 81 and going to network 91. We have created a simple numbered extended access list with two entries by using the access list command. Now, let's create one more numbered extended ACL using the IP access list command. As mentioned earlier, the IP access list command does not detect the ACL type automatically. We need to specify the type manually. Specify the type as extended. To create a numbered extended access list, we use the number here. To create a named extended access list, we use the name here. Let's create a numbered extended access list first. As we know, the IP access list command usages the sub-configuration mode to add entries. When we hit the Enter key, the command places us in sub-configuration mode. In sub-configuration mode, we can add new entries to the ACL and manage existing entries. Let's add two new entries. This entry will block all traffic coming from network 100 and going to network 110. This entry will allow all traffic coming from network 101 and going to network 111. Now, let's create a named extended access list. Specify the name here. Add two ACL entries. This entry allows IP traffic coming from network 110 and going to network 115. This entry denies IP traffic coming from network 110 and going to network 120. To verify ACLs, we need to go back to privileged mode. Now let's check all extended access lists. Here are all the extended access lists that we created. We can apply an extended ACL to an interface from its interface configuration mode. Let's apply ACL 120 to Gigabit Ethernet 0/0/1 interface in the inward direction. Now the router will use this ACL to filter all incoming traffic. If a packet is coming from network 101 and going to network 111, it will forward the packet. If a packet is not coming from network 101, it will drop the packet. We can use the show running configuration command to confirm the implementation. As you can see, router has applied this ACL to the interface. If entries of an extended ACL have sequence numbers, you can edit them in the sub-configuration mode of the IP access list command. For example, let's add a new entry before this entry in this ACL. To add a new entry before an existing entry, we need to use a lower sequence number for it than the existing entry has. Let's switch back to privileged mode and use the show IP access list command to view the updated ACL. As you can see here, the router placed the new entry before the existing entry. To delete the entire ACL, we use the no command in global configuration mode. We need to specify the name or number of the ACL with the no command. Let's delete this ACL. This command deletes the entire ACL. To verify that the ACL has gone, we can use the show IP access list command again. As you can see here, the ACL allow marking has been deleted. To delete a single ACL entry from the ACL, we use the no command in the sub-configuration mode of the IP access list command. Let's delete the entry having sequence number 10 from ACL 120. In the sub-configuration mode of the IP access list command, you don't need to type the entire entry with the no command. You only need to type the sequence number of the entry that you want to delete. To verify that the entry has been removed, view the access list again. As you can see here, the entry has been deleted. We will create a simple network. In this network, we will add 3 LAN segments. To connect LAN segments, we will use a router. Open Packet Tracer. Click the Network Devices icon. Select a router and drag it to the workspace. Click the switch icon and select a switch and drag it to the workspace. Let's add one more switch. Click the End Devices icon and drag 6 PCs to the workspace. Whenever you drag a device icon to the workspace, Packet Tracer adds that device to the workspace. To add the same device again, we need to drag it again. Now add a server to the workspace. To connect these devices, click the Connections icon. Select the copper crossover connection type. Right-click the router, select Gigabit Ethernet 0/2 interface, right-click the server, and select the Fast Ethernet 0 interface. Now select the copper straight-through connection type, right-click the router, select the Gigabit Ethernet 0/1 interface, right-click the switch, and select the Gigabit Ethernet 0/1 interface. Repeat the same process and connect the router's Gigabit Ethernet 0/0 interface to the switch 1's Gigabit Ethernet 0/1. Now connect PC 0, 1, and 2 to switch 0. To connect PCs to the switch, you can use any free port. Connect PC 3, 4, and 5 to switch 1. Now, this network has 3 LAN segments connected through a router. This is the teacher segment. This is the student segment. This is the server segment. To use these LAN segments for testing, we need to assign an IP configuration to each device. In this segment, we will assign an IP configuration to each device from the network 10.0.0.0/8. For this segment, we will use network 20. For the server segment, we will use network 30. A LAN segment uses the default gateway to connect to the remote network. A default gateway is the router's interface connected to the LAN segment. To provide connectivity between the LAN segment and the default gateway, we must use an IP configuration for the default gateway from the LAN segment's network. Let's assign an IP configuration to each gateway interface. Click Router and click Config. Click Gigabit Ethernet 0/0. This interface is the default gateway of network 10. Since this interface is the default gateway of network 10, we must use an IP configuration from network 10. By default, a router keeps all interfaces in the powered off state. To power on it, click On. Click Gigabit Ethernet 0/1. This interface is the default gateway of network 20. Let's assign an IP configuration from network 20. Turn on the interface. Click Gigabit Ethernet 0/2 and assign an IP configuration from network 30. Turn on the interface. Now, wait for a few seconds. Let the network converge. Once all connections turn green, the router is ready to provide connectivity between LAN segments. To use LAN segments for testing, we need to assign an IP configuration to every PC in the segment. Click PC. Click Desktop. Click IP configuration. Select Static. Assign an IP configuration from network 10. Use the IP address of the router's Gigabit Ethernet 0/0 as the default gateway IP address. Repeat the same process on PC 1. Now assign the IP configuration to PC 2. Use the same process and assign an IP configuration to PC 3, PC 4, and PC 5. These PCs belong to network 20. So we will use an IP configuration from network 20. The router's Gigabit Ethernet 0/1 connects this segment to other segments. So we will use the IP address of the Gigabit Ethernet 0/1 as the gateway IP address on all PCs of this segment. Now assign an IP configuration to server. It belongs to network 30. So we will use an IP configuration from network 30. We have assigned an IP configuration to all devices. Now, let's test the connectivity between all LAN segments. To test connectivity, we can use the ping command. It sends several packets to the specified destination device. If the destination device is up and reachable, the destination device replies. It prints the result of each packet in the output. If you see reply messages in the output, it verifies that the source and the destination are up and have proper connectivity. As you can see here, PC 0 and server have proper connectivity. Packet Tracer includes a special feature known as simulation. It allows you to view how a packet reaches the destination. Let's use this feature to check how a packet from PC0 reaches to server. Click Simulation. By default, it supports many protocols. If we keep all these protocols selected, we will see lots of packets moving between devices. To view only packets of the ping command, uncheck all these protocols and select only Icmp for IPv4. Now use the ping command again. Click Play button. Now you can view the real-time movement of the packet. The simulation pane also lists each movement here. As we can see here, PC0 and server can exchange data packets. The router is forwarding packets from both networks. It verifies that the student segment and the server segment have proper connectivity. Now, let's test connectivity between the teacher segment and the server segment. To test connectivity, you can use the ping command on any PC of the teacher's segment. As you can see here, the teacher segment can access the server segment. Now this network is ready for the practice of ACLs. At this moment, all LAN segments can access each other. Now suppose, we want to create an ACL that serves the following purposes. Allow the student segment to access the teacher segment. Block the student segment to access the server segment. Allow the teacher segment to access the student segment and the server segment. To fulfill these requirements, we can create a standard ACL or an extended ACL. If we choose a standard ACL, we can use only the source address in ACL entries. But if we choose an extended ACL, we can use both source and destination addresses. We will implement both types of ACLs. Let's start with the standard ACL. To create a standard or an extended ACL, we have two commands, access list and IP access list. Let's use the access list command to create the standard ACL. Click Router and click CLI to access the command prompt of the router. We can create an access list only in global configuration mode. To enter global configuration mode, we use the enable and configure terminal commands. To create a new standard ACL, the access list command needs a unique number from the predefined range of numbers. Let's use the number 10 here. Now, we need to specify the action. To block all traffic from the network, we will use the deny keyword here. As I mentioned earlier, a standard ACL can only filter traffic based on the source address. Here, we need to specify the source address. To block the entire segment, we will use the network address of the segment. To include all hosts of the segment, we will use the Wildcard Mask 0.255.255.255. By default, all ACLs have a default implicit deny statement at the end. This statement becomes active as soon as we add the first entry. Because of the implicit deny statement, we have to add a permit statement for the teacher segment. If we will not include a permit statement for the teacher segment will also be blocked by the default implicit deny statement. This entry will block all data packets having the source address from network 10. This entry will allow all data packets having the source address from network 20. Now, this ACL is ready. But it will do nothing until we apply it to an interface. We apply a standard ACL close to the destination. So it does not block the source from accessing the other segments of the network. For example, if we apply this ACL on gigabit Ethernet 0/0 in the inward direction, the student segment will not be able to access any other segment of the network. To block the student segment from accessing the server segment, we need to apply this ACL on the gigabit Ethernet 0/2 interface in the outward direction. To apply an ACL to an interface, we use the IP access group command. This command needs only two arguments, the ACL number and the direction. Now, this ACL will block all outgoing data packets if they have the source address from network 10. To verify that we have created and implemented ACL correctly, we can use the ping command again. To view the real-time movement of packets, we can also turn on the simulation mode. As we can see here, before the ACL implementation, this PC could access the server segment. Now send the ping request again. As we can see here, the router is not allowing this packet. If a router does not forward a data packet, it sends an Icmp error message back to the sender. From this message, the sender device can learn that the destination device is not reachable. We blocked the students section only from accessing the server segment. We did not block it from accessing the teachers segment. To verify it, let's send ping requests to a PC of the teachers segment. As we can see here, the router is not blocking a data packet going to the teachers segment. Here we get the reply from the destination device. It verifies that the student segment can access the teacher segment. We have verified our first requirement. Now let's test the second requirement. Our second requirement says it should not block the teacher's segment from accessing the server segment. To verify it, we can send ping requests to server from a PC of the teacher's segment. As we can see here, the router is not blocking the teacher's segment from accessing the server segment. Here we get the reply. We can also use the show IP access list command to check the number of packets matched against each entry. Now suppose, instead of blocking the entire server segment, we want to allow some services running on the server to the student segment. In that case, we have to use extended ACLs. A standard ACL can't filter application-based traffic. Let's suppose we want to allow the student segment to access the web server running on the server. For this practice, we don't need any additional setup. The server includes a web service. By default, this service is running. To test this setup, we can access a web page from a PC of the teacher segment. As we can see here, the PC can access the web service running on the server. Let's try to access the same web page from the student segment. At this moment, the student segment cannot access the web service. Can you guess why? Because we implemented a standard ACL on the router that is actively blocking all traffic coming from the student segment and going to the server segment. To allow access, first, we need to delete this ACL. Access the CLI prompt of the router and enter global configuration mode. To delete an ACL, we use the no access list command in global configuration mode. This command needs the ACL number. To verify that the ACL has been removed, we can use the show access list command in privileged exec mode. Here we can see that the ACL has been removed. Now, let's access the web page again. Now the PC from the student segment can access the web page. But, it can also access the other services running on the server. To verify it, let's send ping request to the server again. Ping replies verify that this PC can access other services running on the server. Now, let's create and implement an ACL that allows the student segment to access only the web server running on the server. As I mentioned earlier, a standard ACL can't filter application-level traffic. To filter application-level traffic, we need to use an extended ACL. Let's create and implement an extended ACL. We can use both the access list or the IP access list command to create an extended list. Let's use the access list command first. Specify a number from a predefined number range for the extended access list. To allow access, we use the permit keyword here. Since we want application-level filtering, we will use the protocol that transports the data of the application. TCP protocol transports web traffic. Use TCP here. Now, we need to specify the source address. To filter data packets of the entire segment, we will use the segment's network address. To specify all hosts of the network, we will use the Wildcard Mask 0.255.255.255. If you want to filter data packets originating from a specific application, you can specify the application's port number here. Our requirement says we need to allow the student segment to access the web server running on the server segment. It does not mention a particular service or application that can access the web server. Since it does not mention any particular application, let's allow all applications. To allow all applications, do not specify any port number here. The default criteria include all applications. Now specify the destination address. You can specify a particular host or all hosts of the segment. To specify a single host or all hosts of the network, we use the Wildcard Mask. Let's include all hosts of the destination network. Now, we need to specify the application. Our requirement clearly says we need to allow only web traffic. TCP protocol uses two protocols HTTP and HTTPS to transmit web traffic. HTTP transmits data on port number 80 whereas HTTPS transmits data on port number 443. The main difference between both protocols is HTTPS transmits data securely. Let's specify port 80 first. Now use the same command again and specify the port number 443. These two entries will allow all web traffic originating from the student segment and going to the server segment. Now we need to block all remaining traffic. To block all remaining traffic, we use a deny entry. Since we are blocking all traffic, we will use the IP keyword here. Specify the source network address and the destination network address. This ACL entry will block all traffic originating from the student segment and going to the server segment. While adding ACL entries, you need to pay extra attention to the order of entries. A router always processes ACL entries from top to bottom for every packet until a match is found. Once a match is found, the router does not check the remaining entries for the packet. Because of this, when the router receives a data packet from the student segment going to the server segment, it checks the destination application. If the destination application is the web server, it allows the packet. It does not check the next entry. It checks the third entry only if the destination application is not the web server. It uses the first entry to allow non-secure web traffic, the second entry to allow secure web traffic, and the third entry to deny all remaining traffic. If we implement this ACL in the current state, because of the implicit deny statement, the student segment will not be able to access other segments of the network. To allow the student segment to access the other segments of the network, we need to add an allow entry. Specify the student segment's network address. You can use the any keyword in the destination address field to allow access to all segments. This entry will allow all packets originating from network 10 and going to network 30 for the web server on port 80. This entry will allow all packets originating from network 10 and going to network 30 for the web server on port 443. This entry will deny all packets originating from network 10 and going to network 30. Since web traffic has been already allowed, it will deny only the remaining traffic. This entry will allow all packets originating from network 10 and going to any network. The router will check this entry only if the destination network is not 30. If the destination network is 30, the packet will be processed by previous entries. We apply an extended ACL close to the source. This practice stops unwanted traffic as soon as it enters the network. We will apply this ACL to the gigabit Ethernet 0/0 in the inward direction. To test this ACL, let's access the web page again from PC 0. As you can see here, we can access the web server using the HTTP protocol. Now let's use the HTTPS protocol. We can access the web server on both protocols. Now let's try to ping the server. It should be denied. As you can see here, we are not allowed to access any other service running on the server except the web service. Now, let's test the connectivity with the teacher's segment. Send ping requests to a PC of the teacher's segment. Here, we get the reply. It verifies that the student segment can access the teacher's segment. We can also check how many packets were filtered by each ACL entry. To view the number of data packets matched against each ACL entry, we can use the show IP access list command. We can see the number of packets matched against each entry here. We have learned how to create, implement and verify standard and extended ACLs. Now, let's build a complex network. Add 3 routers to the workspace. I am adding a 2911 series router. It has 3 gigabit Ethernet interfaces. You can add any other router. Now add 5 switches. We will use these switches to connect the LAN segments to the routers. We will not change any setting or configuration of the switch. Now connect these devices. To connect a router to a switch, we use a copper straight cable. Connect the router's gigabit Ethernet 0/0 to the gigabit Ethernet of the switch. Connect the gigabit Ethernet 0/1 to this switch's gigabit Ethernet. Now connect the second router to this switch. We will connect the second router to only one switch. Now let's connect the third router to these switches. To connect a router to another router, we use a copper crossover cable. Connect router 0's gigabit Ethernet 0/2 to router 1's gigabit Ethernet 0/2. Connect router 1's gigabit Ethernet 0/1 to router 2's gigabit Ethernet 0/1. Now add some end devices for testing. Add 6 PCs and 2 servers. Connect 2 PCs to a switch. To connect PCs to switches, use the automatic connection type. It will automatically add the necessary connection between the PC and the free port of the switch. Since we will not make any change on the switch, it doesn't matter which switch port it uses to connect the PC. We are using switches only to connect LAN segments. Connect servers to their switches. Now we need to assign IP configurations to these devices. We will use this IP configuration. Click PC. Click Desktop. Click IP configuration. Assign the IP configuration. Repeat the same process. A LAN segment uses the router's interface as the default gateway. Generally, we do not use a flat IP configuration scheme for networks. We use VLSM to optimize the use of IP addresses. To use VLSM, we have to do a lot of additional calculations. Since the IP configuration scheme doesn't affect ACL implementation, we can use a flat IP configuration scheme for each LAN segment. If we use a flat IP configuration scheme, we need a separate IP address space for each LAN segment. That's not a good choice in real-life network. But in the lab environment, it's perfectly fine to use flat IP configurations for LAN segments. A flat IP configuration scheme allows us to test more networks. For example, this scheme allows us to test 7 different networks. These networks are 10, 20, 30, 40, and 50. We will use networks 60 and 70 to connect routers. To keep this example simple, we will not change any configuration on switches. We will use all switches with their default configuration. With default configurations, a Cisco switch works as a regular Layer 2 Ethernet switch. Now we have assigned IP configuration to all end devices, let's assign the IP configuration to routers' interfaces. This interface works as the default gateway for network 10. Let's assign an IP address from network 10. This interface is the default gateway of network 20. Assign an IP address from network 20 and turn it on. This interface connects the router to router 1. We will use network 60 to connect this interface to router 1's Ethernet interface. If we have multiple routers in the network, we have to use a routing protocol to connect them. A routing protocol allows routers to share routing information. RIP is a basic routing protocol. Packet Tracer allows us to configure it directly from here. To configure this protocol, add all the networks this router knows. We have added networks 10, 20, 60 to the RIP protocol. Now, the RIP protocol will automatically broadcast these networks to other routers of the network. Let's repeat the same process on router 1 and assign IP configurations to all interfaces. First, assign an IP configuration to gigabit Ethernet 0/2. It connects the router to router 0. Now, assign an IP configuration to Gigabit Ethernet 0/0. It works as the default gateway for network 30. Gigabit Ethernet 0/1 connects the router to router 2. Assign an IP configuration from network 70. Now, we need to add these networks to the RIP protocol. Now, let's assign IP configurations to router 2. This interface connects the router to router 1. Assign an IP address from network 70. This interface is the default gateway of network 40. Assign an IP address from network 40. This interface connects the network 50. Assign an IP address from network 50 and turn it on. Add these networks to the RIP protocol. Now let's test this network. To test it, we can use the ping command. Open the command prompt of PC0. Ping the default gateway. Ping replies confirm that the PC can access the default gateway. Now ping a PC of network 20. As we can see here, the PC is connected to network 20. Now send ping requests to a PC of network 30. Here we can see that the PC has connectivity with network 30. Here we get the reply from network 40. And finally, here is the reply from network 50. Now this network is ready for the practice of ACLs. Let's suppose we want to create ACLs for the following purposes. Network 10 can access only network 20. It cannot access other segments of the network. Network 20 can access network 10. It cannot access network 30. PC2 can access only web service running on server 0. It cannot access other services running on the server. PC3 can access only the FTP service running on server 1. It cannot access any other services running on the server. Only PC4 can open Telnet connection with router 0 for management purposes. Now, let's create and implement ACLs for these requirements. Our first requirement says network 10 can access only network 20. It cannot access other segments of the network. Except for network 20, data packets originating from network 10 can reach other segments of the network only when they exit the gigabit interface 0/2 of router 0. To reach network 20, they do not need to exit this interface. If we create a standard ACL that denies all outgoing traffic from network 10 and implement it on the gigabit Ethernet 0/2 interface of router 0, we will achieve this goal. Let's create and implement this ACL. In the previous example, we used the access list command. This time, let's use the IP access list command. To deny all traffic of this network, we will use deny action. To include all hosts of the network, we will use the subnet mask 0.255.255.255. Apply this ACL to the gigabit Ethernet 0/2 interface in the outward direction. To test this ACL, open the command prompt of PC0. Now send ping requests to a PC of network 20. Here you can see, this PC is allowed to access network 20. Now, let's try to access networks 30, 40, and 50. As you can see here, this PC is not allowed to access any other segment of the network. We can also use the show access list command to view the number of blocked packets by the ACL. We sent a total of 12 ping requests from PC0 for other segments, and all of them were blocked by this ACL entry. At this time, this ACL has a big problem. This ACL will block all traffic passing through the interface. To verify it, let's try to ping network 30 from network 20. Here you can see we are not allowed to access network 30. Now try to ping network 20 from network 40. Can you guess why this is happening? This is happening because we created and implemented an ACL that is only a deny statement. An ACL having only the deny statements block everything. To allow the remaining traffic, we need to add a permit statement at the end of the ACL. Let's fix this issue. Now, test the ACL again. As we can see here, PC3 can access network 30. It verifies that the ACL is not blocking the traffic of other networks. You can also send ping requests from server 0 again to confirm that ACL is not blocking the traffic of other networks. Now test from PC 0 again. Besides network 20, it should not be allowed to access any other segments of the network. As we can see now, this ACL is preventing network 10 from leaving the interface, but it is not blocking the data flow of other networks. That's exactly what our first requirement says. Our second, third, and fourth requirements are related to network 20. The third and fourth requirements need application level filtering. Only extended ACLs can filter traffic based on applications. Because of this, we will create an extended ACL. We apply an extended ACL near the source. The nearest interface of network 20 is the Gigabit Ethernet 0/1 interface of router 0. This interface is the default gateway of the network 20. If we apply an extended ACL on this interface in the inward direction, all unwanted traffic from network 20 will be filtered as soon as it enters the network. Let's create an extended ACL for these requirements. Our second requirement says network 20 can access network 10 but it cannot access network 30. For this requirement, we need to add two statements. In the first statement, we will allow network 20 to access network 10. Let's create a statement for this. First, we need to specify the action. Since we are creating an allow statement, the action will be the permit keyword. Next, we need to specify the type of filtering. To filter all data packets from the source, we will use the IP keyword here. Now specify the source address. Since we want to allow the entire network, we will use the network address. Now we need to specify the destination address. This statement will allow all data packets that have the source address from network 20 and the destination address from network 10. Now let's add a statement that denies network 20 from accessing the network 30. This statement will deny all data packets having the source address from network 20 and the destination address from network 30. Our next requirement says PC2 can access only web service running on server 0. It cannot access other services running on the server. For this requirement, first, we need to add a permit statement that allows PC2 to access web service running on server 0. Use the permit keyword to allow access. To filter data packets of a particular application, we use the name of the protocol that transports the data of that application. Web service uses the TCP protocol to exchange data packets. We are creating this statement only for a single host. For this, we will use the Wildcard Mask 0.0.0.0. The Wildcard Mask 0.0.0.0 is used to specify a single host. After the destination address, we need to specify the port of the web service. The web service uses two port numbers 80 and 443. To allow traffic on port 443, we can add the same statement again after changing the port number. Now, we need to add a statement that blocks PC2 from accessing the other services running on server 0. Since we are blocking all remaining traffic, we will use the IP keyword here. Now specify the source and destination address. These three statements will allow PC2 to access only the web service running on server 0. If PC2 will try to access the web service running on server 0, these statements will grant access. The router will never check this statement if the data packets are coming from PC2 and going to the web service running on server 0. The router will check this statement only if the data packets are coming from PC2 and not going to the web service running on server 0. After these statements, the router will allow PC2 to access only the web service running on server 0. This is exactly what our third requirement says. Our next requirement is similar to the third requirement. For this requirement, we can use the same statements after changing the source address, destination address, and port number. The FTP service uses port number 21 to establish the connection and port number 20 to exchange data. Now let's add a statement that blocks PC3 from accessing the remaining services. These statements will allow PC3 to access only FTP service running on server 1. Now we need to add a statement that allows all remaining traffic. If we do not add this statement, the router will block all remaining traffic. Remember the implicit deny statement. Routers automatically add an implicit deny statement at end of each ACL. The implicit deny statement denies all traffic that does not meet the preceding statements. Now let's implement this ACL. We will implement this ACL on the Gigabit Ethernet 0/1 interface. This interface is the default gateway of network 20. We will implement this ACL in the inward direction. Now let's test this ACL. First, send ping request to network 10. It must be replied. Here you can see that we get replies from a PC of network 10. It verifies that network 20 can access network 10. Now try to access network 30. It must be denied. As you can see here, this PC is not allowed to access a PC of network 30. To test the third requirement, first, we will send ping request to server 0. It should be denied. Now open the web browser and access the web service running on server 0. As you can see here, This PC can access the web service running on server 0 on both ports 80 and 443, but it cannot access any other service. To test our fourth requirement, open the command prompt of PC3. Now send ping request to server 1. Here you can see the ping requests are denied. By default, the FTP service is enabled on server. The default username and password are Cisco and Cisco. Open an FTP connection. Use some FTP commands. It verifies that this PC can access and use the FTP service running on server 1. Let's send ping requests one more time. As you can see here, it cannot ping server 1. It verifies that this PC can access only the FTP service running on server 1. It can't access any other services running on server 1. Our last requirement says only PC4 can open telnet connection with router 0 for management purposes. Cisco routers support the remote management feature. For this feature, routers use virtual type terminals. When you access a router remotely, the router associates the remote connection to a virtual type terminal. You can use the assigned virtual terminal to execute commands. Routers support multiple remote connections simultaneously. To keep each connection separate, routers assign a unique number to each connection. These numbers are known as VTY line numbers. VTY line numbers start from 0. To access VTY lines, you need to use a remote management protocol. Routers support 2 protocols for remote management. These protocols are Telnet and SSH. By default, both protocols are installed on Cisco routers. You can use one or both of these protocols to access the router's virtual terminal. Since these protocols involve security risks, routers do not enable them automatically. If you want to use these protocols, you have to enable them manually. No matter which protocol you enable for virtual terminals, access lists work similarly for both protocols. Since our requirement needs Telnet, let's enable Telnet. Routers use the line configuration mode to manage all connection lines. By default, a router supports 5 VTY lines. Enter VTY line configuration mode. To set a password, we use the password command. This command will set a password to Telnet. To enable Telnet on all lines, enter the login command. That's all we need to enable Telnet connections on the router. Once enabled, you can use any active IP address on the router to access the router's virtual terminal. Telnet uses the password to authenticate the user. It does not authenticate the client system. It means any user who knows the correct password can log in from any client system. To verify this, open the Telnet client program of PC2. Specify any one IP address from the active IP addresses on router 0. We have 3 active IP addresses on the router. Use any one IP address from these IP addresses and click the Connect button. Enter the password that you configure with the password command when enabling Telnet sessions. Here we get a virtual terminal. From here, we can manage the router. To secure virtual terminals or permit only particular IP addresses to access them, you can use a standard ACL. Let's create and apply a standard access list to secure VTY lines. Specify the IP address of the host which you want to allow. In line configuration mode, we use the access class command to implement the ACL. Apply ACL in the inward direction. To verify the ACL implementation, access the router's virtual terminal from PC2 again. This time the router should not let you access the virtual terminal. Here we can see that PC2 is no longer allowed to access the virtual terminal of the router. Now try to log in from PC4. As we can see here, PC4 is allowed to open a virtual terminal line. You can also use the Show IP Access List command to view the number of packets filtered by the ACL. That's all for this video. In this video, we learned how to create, implement, and verify standard access lists and extended access lists on Cisco routers. If you have any suggestions, comments, or feedback about this video, please share them in the comment box given below.